For this part, I'm going to introduce about the generation method for key phrases. So, okay, recall that we have introduced the concept of absent key phrases in the part one. So the absent phrases denotes that the phrase which don't appear as a substring of the source text. In fact, the annotators assign key phrases by their importance or relevance to the document, not by whether they appear in the text or not. So in that sense, by checking the data in the real world, we can see that a large proportion of the phrases are actually absent. So you can see this is the ratio of the present phrases in these 6 data sets. And in some data sets, more than half of the phrases are actually absent. And which means all of those absent phrases, there's no way to be predicted by the most extractive methods we have introduced so far. But before we get into the technical solutions for predicting absent phrases, let's first take a look at about what the absent phrases are like. So one way to categorize those absent phrases is by checking the lexical overlap between the source text and those phrases. So in that way, we can group them into three types. So for the reordered is the both words, all the words of the phrases that can be found in the text, but we just shuffle their order in the phrase. And by mixed, what we mean is some words can be found in the text, so which means the phrases can be partially found in the text. And by unseen absent phrases, which means all the words do not appear in the source document. And another way to understand those absent phrases is those phrases can be just some high-level concepts. So in that way, we don't see them in the source text, and sometimes they are just synonyms or acronyms of present phrases. So, for example, if the e-commerce appears in the source text, but the annotator may also assign the electronic commerce as a keyword to this document. So in this case, the electronic commerce is also an absent phrase. And some special case, for example, the beginner is also a very popular key phrase in Stack Exchange, which denotes, okay, this question is raised by a beginner, so it talks about something really basic. So you can see absent phrases, they play a very important roles. They describe the content or some certain aspects of the document. It can be high level, and it can be describing something really unique, which are very different from the generic, the role of present phrases. All right. So now let's turn our attention to the main topic of this part, which is neural key phrase generation. So since both source text and the target phrases can be seen as sequences of tokens, then we can cast it to a sequence-to-sequence learning paradigm, which means an encoder is utilized to convert the source text into an intermediate embedding. Then we use another neural network as decoder to predict the key phrases as another sequence or multiple sequences. So you can see this sequence-to-sequence learning is very similar to machine translation and summarization. But, okay, and this is the taxonomy of the generative methods we will be talking about. And since the training paradigms of all the generation methods can be categorized as those three types, and we will start by introducing them first. And basically, the major difference of those training paradigms just lie in the format of the output during training. So you can see why it's just decided by how many phrases we output by the decoder. And so we will first talk about the one-to-one paradigm. So in this way, this is a common format of a data example of a document and its corresponding key phrases. And in this one, we assume it comes with key target phrases, and to convert it to a one-to-one training pairs, we copy and paste the original source text by k times, and each is paired with one single target key phrase. And you may notice that the original data points now becomes k data points, and which means it results a huge waste during the training. And during the training, at each time, the decoder only needs to generate one phrase at a time. So the benefit is the decoder can be really, can capture the phraseness very well, since it only needs to care about generating one phrase at a time. But however, during the inference and evaluation, we need the model to generate multiple phrases because usually given one document, we need multiple key phrases to summarize its content. So this leads to a very important design in the key phrase generation, which is to leverage the beam search for inference to generate a large number of unique phrases. And the one-to-one models can easily generate more unique phrases by using a large beam width. For example, given one document and a large beam width, it can generate, say, more than 200 unique phrases. And this results in a really good performance on predicting absent phrases. But it has downside. So for the inference of one-to-one paradigm, since all the phrases are generated independently, and they are only ranked by the likelihood of each sequence. So in some cases, a very important word, for example, here is the Jackson, can dominate the final predictions and show a really bad diversity in the generated phrases. Then let's take a look at the other paradigm, the one-to-seek. So during the data preparation, it's more straightforward. We can simply concatenate the k target phrases as a sequence and delimited by a special token here is the SEP, separator. But keep in mind, the way we concatenate those target phrases can affect the eventual performance drastically. And we will show the results later. And for the training, it's also very straightforward. Since multiple phrases are generated, we just simply feed the document and train the decoder to generate multiple phrases as a single sequence. And you can see that since the model, the multiple phrases are generated in an autoregressive way, So the model can try to avoid generating the semantically similar phrases that has been generated already. So, but this advantage of avoiding generating similar phrases is only available when we are using the greedy decoding in inference. So which means only single sequence is generated. So for example, in this example, this single sequence only has 3 key phrases. So in some cases, if we need more phrases, we still need to utilize the beam search. But in this case, the 1-to-6 paradigm, the inference is not really good. That's because when we are using the large beam width, actually the resulting sequences actually contain a lot of duplicated phrases. So for example, here, if we use a beam width of 50, in some results, almost 99 of the generated phrases are duplicates. So which means only 1% of the phrases, after we aggregate all the generated phrases, only 1% of them are unique. So this is really inefficient. So there's one more design that has shown great effects in the performance of the Keyphrase generation, which is called copy attention. So simply speaking, we just besides this abstractive way that we encode the information into an intermediate encoding and decode the information given this bottleneck in binding. We also utilize another attention mechanism to directly copy the relevant words from the source text and output it as phrases. And we can take a look at the evaluation results of this copy attention mechanism. So it's very clear that when the copy is enabled, it results a huge boost on the model's performance on predicting present key phrases for both 1-to-1 paradigm and for both RNN architecture and the transformer. So you can see for the absent. But in some cases, especially for the transformers, it's very interesting to see that the copy can hurt its abstractiveness. So which means for predicting absent phrases, by enabling the copy mechanism, the performance of generating absent phrases is becoming worse. All right. So as for the comparison to traditional baselines, we can see the key phrase generation models outperform them by a really large margin. What's the reason? I think the one reason is since the model learned the ranking, how to rank the predicted phrases by the likelihood that which is directly learned from the data, instead of relying on human designed crafted rules or features. And another reason is the better phraseness. So the generation models learns a better idea about the morphology of the phrases. So for example, on the left side, the phrase candidates are obtained by the non-phrase extractor, which contains some noisy and trivial phrases. And the TF-IDF just ranks some really common or even trivial words to the top places. But on the right side, you can see the output of the key phrase generation models are more phrase-like. You see it contains multiple words, and the most important phrases are ranked to the top places. All right, so recall that when I was introducing the 1-to-6, we can concatenate the target phrases in different orders. And now I'll show you that that order can be consequential in the final performance. And here we empirically experimented with several different ways, different order of the concatenation. So for example, here, by the present absent, which we mean we just put the present phrases at the beginning and append the absent phrases after that. And the ABS pri-ES is just concatenate the absent phrases and the present phrases in another way, in the reverse order. And this shows the result. So for both RNN models, so the top is RNN, the bottom is based on transformer, certain orders do outperform the others, but especially for the present absent order, its performance is the best among all. And very interestingly, the self-attention of the transformer doesn't really make it more robust against the different order of the concatenation. This suggests that the order, how we concatenate those phrases, may carry certain inductive bias that can affect the training. And you can see the gap between different order is really huge. It's not really something can be ignored. So a natural way to eliminate such effect of ordering is by removing them during training. And this leads to the third paradigm, which is called one-to-set. So one-to-set model, during the training, they just replace the autoregressive decoding by a non-autoregressive way. You know the transformer, they can be implemented as a non-autoregressive decoder. And then the Hungarian algorithm is also used to align the order of the target phrases dynamically. So in this way, during the training, the model is not aware of, okay, which phrase should be generated before another one. So all the phrases are just treated as a set. Okay, so now we have seen three most influential paradigms for training the Keyphrase generation models. Yes, yet there are still many problems haven't been solved nicely, and we expect to see better modelings to become available in the future. And now we switch the gears a little bit and take a look at some other successful generation models. So far, all the phrases, Keyphrase generation models are trained with the maximum likelihood estimation, so short for MLE. So which means the goal of training this model is to maximize the probability of the next word. However, in the evaluation, what we really care about is the F-scores usually for the Keyphrase task. And its goal is actually to maximize the overlap between the goal phrase set and the predicted phrase set. So how can we make the model be aware of this phrase level loss, phrase level objective during the training? And the key is using the reinforcement learning. So for example, here, after we have completely generated the target sequence, we can compute a global word. So in this case, we can use just the F1 score. And then we optimize the whole model with a technique called policy gradient. So in this way, the model is trained to not only maximizing generating each word, but also to maximize the eventual evaluation scores. And there are two papers trying to improve the Keyphrase generation in this way. And the first paper designed a reward manually, and another paper used the GAN to learn a reward function from the data directly. Another interesting line of research for the keyphrase generation is to use the retrieved documents as augmentation. So for example, in this paper, given a source text X, a retriever just retrieves similar documents based on some traditional retrieval models such as BM25. Then we use the associated key phrases as external hints, and which will help the generator to generate some to generate the eventual key phrases. And the right side, the table shows the ablation result of move enabling the retrieval module. The RK is the retriever. So you can see by comparing the results of with and without the retriever part, the absent phrases, the performance of absent phrases drops very drastically. So which means the retrieved documents indeed helped a lot for the generator to predict phrases, especially if they are absent phrases. And another application of the retrieval augmentation is for the multilingual key phrase generation. So in this setting, we assume we have abundant documents with annotated phrases in English. And the goal is to generate the key phrases for documents in other languages, such as French and Dutch. And then here, we can just use a multilingual dense retrieval model, such as MBERT. So given a document in French, we just retrieve similar documents in English and use the corresponding English phrases as hint to help the generator know, okay, what phrases can be relevant and to generate them. And this study is just, it also contributed to new data sets for the setting of the multilingual key phrase generation. And one is based on the scientific papers, and another one is based on the Amazon product search. I think it's an interesting data set and will be available soon. Okay, and the next study I feel is very interesting to share is the first attempt of training an unsupervised generation model. So for unsupervised methods, so far what we are very familiar with are extractive methods. So why there are so many extractive models that can be unsupervised? So I think the reason is, first, it's relatively easy to extract some candidates from the source text, say by utilizing the n-grams and noun-phrases. And what's next? We can just use some heuristics, unsupervised scoring functions such as frequency, like TF-IDF, and graph-based features to rank those candidates. So you can see both steps, they don't need supervision. So can we do something similar for training a generation model? So in this study, the core idea of unsupervised generation is actually very similar to what I just talked about in extraction models. So here we need to construct pseudo text key phrase pairs to train a generation model. So the first step, similarly, we are going to extract all the noun phrases from a large document collection to build a phrase bank. And then given a new document, we just assign the absent candidates by checking, okay, whether there's any word overlap. So in another word, we are seeing what I'm saying is if a candidate phrase partially overlap with the given document, we just treat it as an absent phrase candidate. And for the present one, it's very simple. We just extract all the noun phrases in that document as the present candidates. And then the second step, we are just utilizing two scoring functions. One is lexical, one is semantic, to rank all those phrase candidates. And in this way, we can obtain top K present phrases and top K absent phrases. And we just take them as the synthetic pairs and use them to train a sequence-to-sequence model. It's just the way we have done with all the previous generation models. But in this study, we are using synthetic pairs, not the data pairs annotated by humans. So another way to think about this method is it actually is a knowledge distillation process. So we just rank those data pairs by the keyness and phraseness, and we just hope the neural networks, the sequence-to-sequence model, are able to acquire the key-phrase knowledge from the data, and then it can generate good key phrases. And let's take a look at the result. So on the present phrases, the generation model can outperform all the traditional baselines very easily, but still we can see there's a gap between the unsupervised model and the supervised counterpart. But in certain cases, the unsupervised model performed a little somehow better. And as for the absent key phrase prediction, the model indeed can predict some correct absent phrases, but still far from usable for real applications. So you can see there's a huge gap between the supervised one and the unsupervised one. But still, I think this study is really a good start. We are trying to explore more ways to get rid of the data reliance. I mean, especially on the annotations. Okay, so the last part of this generation model, some studies trying to combine the best of both worlds. This is because people found that the extraction models are usually more reliable, whereas the generation models are more expressive. So can we consider combining both, and maybe it can result a better performance? So a common way to achieve this idea is we first utilize an extractive module to extract some present phrases, as for example here as a sequence labeling in a sequence labeling way. Then we just pass the extracted results to the generator, and in this way the generator knows, okay, what phrases in the source text are more important. Then they take the generator takes those phrases as hint, and in this way to generate better eventual phrases. And the empirical results shows that usually by combining both extraction and the generation, the final result is usually better. And we have seen already several studies have been following this paradigm. Okay, so to quickly sum up, so the deep learning methods have achieved great success for the key phrase, both extraction and generation, and mostly owing to the ability of learn to predict good phrases in a fully data-driven manner. But it also has many shortcomings. such as it's super heavy data dependent, and the overall quality of the generated absent phrases is also very poor. So we look forward to seeing better models and more methods in the future. Okay, and the next part would be about the introduction to some code bases for deep learning based Keyphrase studies. So the OpenAMT KPG is a package built based on the OpenAMT. And I was having a lot of good time with this package. And I just want to share some features I think that are quite valuable. So the first thing is, I think it's very handy because all the training arguments can be configured in the YAML files. And if you want to start a training, actually it's just a single one line. So you can see the YAML file just configures everything in a really good structured way. We can set what's the pre-trained checkpoint we want to use to initialize the training. What's the metadata of this experiment, the name, the path of the input, output, and what's the name of the 1DB. It's a really useful tool to keep track on the training progress. And then it's something about the data as well as the special configurations for the key phrase. So for example, this specifies the order of the target phrases we want to use. So there are some other orders has also been implemented, such as the random order and also one-to-one. And another very good feature I enjoy a lot is the data pre-processing is completely on the fly. So which means you don't need to tokenize the data and convert it into tensors, save it in the disk additionally. So now we are just reading the data from this JSON file. And you can see we just apply some transform functions on each data example. And so for example here, this is the details of the key phrase function, key phrase transform. And it's just one function, and it will just process all the examples one by one. And what it does here actually is just by taking this example, it will concatenate the target phrases according to the order argument you set here. And then another transform function is also utilized. You see, so here we just utilize the Roberta tokenizer to convert those strings into the corresponding tensors. So it runs very fast, just zero delay. So I also very enjoy this feature. And this is something I developed to help people to reproduce some results. So it's a very simple example, and you can find it in this following this path. So basically what it does is it will load the data set. So for example, here is the inspec. So this data set is maintained by debugging and his group. And all the data is saved online in the Hugging Face repo. And this also specifies a pre-trained checkpoint by me, so which is based on the Wikipedia. And you can see the event, this generates a well-structured performance. And this wiki checkpoint achieves a pretty nice zero-shot performance on the inspec. And if you are interested in, just check it out by yourself. Okay, so that's the end of my part, and I'll just hand the stage to Debajan, and he will introduce the DLKP.
Thank you, Rui.